All right, hello LinkedIn and YouTube. We're doing a LinkedIn live stream today with Luke Marsden. He is the CEO of DotScience, and we're going to talk about machine learning operations, MLOps. So if you're just tuning in, I'd love to hear where you're dialing in from, just so I can get a sense of, who's joining the sessions, where you're joining from. Also, if you could tell me what role you play and if you work with machine learning, that would be really helpful as well. So we'll know which way to direct our conversation. I'm going to quickly go ahead and go into LinkedIn, make sure the stream is working great. And then I'm going to bring in Luke in just about a minute. Okay, looks like the LinkedIn live stream is up, and I see about 20 people are on at this moment. So like I mentioned, let me know who you are, what you do. Do you work with machine learning? What's your involvement in ML ops? And if you have any questions for Luke on machine learning operations, he is here to answer them. All right, I see Jamal says hi. Hello, Jamal. Okay, and while people are tuning in, I'm actually going to go ahead and bring in Luke. Get him started. Hello, Luke. Welcome to the live stream.
Hey, great to be here. Thanks for having me.
And where are you tuning in from?
Bristol, England, in the southwest.
England.
UK. Yeah.
All right. How's the weather / COVID situation over there?
The weather is wonderful. And we've got a bank holiday weekend over the Easter weekend here. So everyone will be enjoying a beer in their own garden if they're lucky enough to have a garden. So I'm looking forward to that.
Awesome. All right. Well, why don't we start with, tell us a little bit about who you are, what you do, how you come to be the CEO of DotScience.
Yeah, sure. So I've done a few startups. This is my third startup, I guess. And I guess the most, I'll kind of start the story at the second one, which was, well, actually, I'll go all the way back. Why not? So my first company was a web hosting company back in 2001. So I started a web hosting company with a friend. We built all of the infrastructure ourselves, all of the software, and then while I was at university, I was intrigued by the challenges of how we would scale that web hosting company up from a technical perspective when we hopefully in the future got lots more customers and needed to cope with dealing with being able to run websites across more than one server and things like that. And so back in the sort of 2000s, that was still kind of an interesting set of challenges. And what I found was that what we did was we started developing this distributed web cluster technology that would allow a cluster of machines to all work together to serve a bunch of websites and to automatically scale up and scale down the capacity and deal with machines failing. And in the course of creating that technology, the team created some interesting technology around clustering, storage, and networking. And so an interesting thing happened, which was that, I don't know, have you heard of Docker?
Yeah, of course. Yeah. Right?
Yeah, Docker containers. And so Docker kind of exploded in a really big way, kind of around, I don't know, I guess it was like 2011, 2012. Maybe a bit later than that, actually. But as Docker was taking off, we realized that the web hosting company that had by that point pivoted to selling software to other web hosting companies, it turned out that a lot of the technology that we built for doing distributed storage was very applicable to Docker because we were actually using a precursor of Docker in the technology stack that we'd used. And so honestly, we found that the web hosting market was kind of shrinking, and a lot of it was being kind of eaten by by like Amazon Web Services and the other cloud providers. And so we were kind of having a tough time selling into web hosting companies. And so we pivoted the company to focus on storage for Docker because Docker was really, really new. And no one had yet figured out how to connect containers to storage in a sensible way for like dealing with databases and things like that. So fast forward a little bit, that company developed that company was called Cluster HQ, and we developed this technology called Flocker that was intended to rhyme with Docker.
Yeah, I was gonna say it sounded something else, by the way, but yes, keep going.
Yeah, you have to be careful with that one. But yeah, so we developed this thing called Flocker, and that was the first storage layer for Docker, and then what happened with that company was that Kubernetes, which you may well also have heard of, it's a container scheduling technology, and it was an open source technology. It grew a lot of the capabilities that we had in the Flocker product, and so we had to figure out how to pivot again. And what we did was we started looking at data versioning in particular, and data versioning for DevOps. Now, Cluster HQ failed spectacularly for reasons that were unrelated to the product or the technology, and that's a whole other conversation. I won't go into that. But I learned a hell of a lot through the failure of that startup, and I then went to work at another company in the cloud native space for a year, a company called Weaveworks, and that was also in the DevOps space. They started out with a networking product, also in the Docker space. But by the time I joined, they were focusing on a bunch of different pieces around monitoring and continuous delivery and all of these things in the DevOps world. I spent a year there. I was very happy there, but I kind of got the itch to do another startup. And so I started this project, .mesh, that was really designed initially to test some of the ideas that we had in the at the tail end of Cluster HQ around data versioning for DevOps. And so what we were trying to do was make it easy for DevOps engineers or for software engineers who are collaborating on an application that they're working on to easily snapshot and move around the state that was associated with that application. So like the contents of databases and file systems and queues and things. And what we realized about 6 months into that project was, okay, there probably is a market for this, and we could build a moderately successful company doing this, but there's a much bigger pain point around data versioning in machine learning and data science. And so we pivoted again. It's kind of the story of my life, is multiple pivots through these different startups. But the interesting thing about data science was that we found there was a lot of talk then, so sort of 2018, 2019, there was a lot of talk then around a reproducibility crisis in data science. And this kind of challenge of, oh, I can make a model, but my colleague can't later make the same model because...
Or I can't do it again later.
Or I can't do it again later, exactly. It's like, oh, I used a Jupyter notebook and I used a data file that I had on my machine, but and maybe I kept a record of what I was doing in a paper notebook or a spreadsheet or something, but I don't. But I have this kind of reproducibility problem, and so we we started trying to solve data versioning for machine learning and data science. So we then we built this this product DotScience on top of the open source project that we developed called .mesh. And so the idea with .mesh was like Git for data. And then .science was like Git for data applied to data science and machine learning. So we started bundling Jupyter, and we started looking at provenance as well as just data versioning, and started looking at run tracking, basically, which is another way of saying experiment tracking. So being able to automatically keep track of the different models that you create and automatically version the different data sets that you use to train them. And so what we found then was that with data versioning and provenance, and very much at that point, so this was kind of early last year, at that point we found that we were really we were focused on the kind of making the training side, the building and the development of models, and making that side of things better and more auditable and improving the tracking in that space. But we also spent a hell of a lot of time trying to sell that into enterprises and doing a lot of enterprise sales. And honestly, what we found was that we spent a lot of time educating people about problems they were going to have in the future. You only actually care about data versioning and provenance and model inventory, like model management, once you get to a certain scale, once you get more than one data scientist working on a problem, once you get more than one version of a model that's being deployed that you need to keep track of, well, where did these different versions come from? And what we found was that a lot of the market, everyone wanted to do AI and ML, but a lot of people were struggling even just deploying models at all into production. They could build models on data scientists' laptops, but their DevOps team or their IT team inside this big company, they were like, what the hell is this Jupyter notebook? Like, what language are you speaking? Like, basically, the IT people didn't know how to deploy data scientists' work. And so there was this large time value between a data scientist on their laptop using Jupyter locally. They can build a model, but they can't actually get it running in production. And so they can't get value, they can't get business value out of that model. Right. And so that was, this is a long story, I know, but it kind of comes up to the current day, which is that what we found was really the market demand was more around MLOps, which is how do I deploy my models into production? How do I monitor the models once they're running in production? And then I care, like once I've got past those hurdles, then I care about data versioning and provenance and model management. So yeah, by making the platform end-to-end, by adding the capability to deploy models and then monitor them, we really started seeing product market fit. And we've seen a lot of new customers come on board in the time since then. So that's kind of how I ended up CEO of DotScience and how I ended up, and how DotScience ended up where it is today.
Great. Well, thank you so much for sharing the story and the journey to, how you got to where you are. We do have a couple of questions that came in on LinkedIn. So let's see. I see we've got T. Scott, Con Daniel, Ravi. Okay, Ravi has a question. So Ravi says, working on creating machine learning REST APIs where a user can enter 0.1 million records and then the API will predict and give the response in the backend. He's using Postgres. How do you say that? Postgres?
Postgres, yeah.
Postgres. Yeah, I never know the right way to say that. He's saying the response time is not good. So any recommendations on what he can do to reduce the response time?
So he says he's posting 100,000 records to this endpoint.
Yes, the API, yep.
Yeah, like 0.1 million.
Yeah.
In a single batch, I guess. I'm curious, but yeah, I'd also want to dig into, well, what framework is he using, and I guess one thing that you could look at is certain machine learning and what kind of model is running in the back end to do this analysis. But as a general point, you might want to try looking at using a machine learning framework that's more highly optimized, or when you're doing REST API endpoints. So I know off the top of my head, for example, that TensorFlow supports TF serving, which is a highly optimized backend for doing inference on models that's written in C++, but in theory is more efficient than something like scikit-learn running in Flask. So yeah, it's difficult to debug the performance issue over a live stream, but yeah, maybe look at more optimized frameworks and I guess just a general approach to performance testing and debugging performance issues is, yeah, try and understand whether the time spent processing the records is like, what's the relationship between the time spent processing the records and the response time. So is it like order n or order log n or order n squared? Because if you have like a a quadratic complexity in, like, basically, if you have to loop over all your data n squared times, for example, to process it, then the more records you add, the slower it's going to get, like, quadratically. So yeah, maybe take a look at some of that kind of big O notation and try and understand the algorithmic complexity of what the model's doing.
Yeah. Okay. Yeah. Thanks for that. Yeah. I guess you'd need a bit more information too.
What I will say is, if you show up on our MLOps Community Slack, then we can chat more after the show. And I can also ask some of the engineers on my team to try and help you out.
Yeah. Speaking of that, so for those who've tuned in, there is an MLOps Community that I can share a link to, where they have weekly meetups. For those that are interested, can join. I can share a link in the comments so people can go check that out. It's MLOps.community, but I'll share it in here as well.
Thanks. And while you're doing that, yeah, we started this about 3 weeks ago because honestly, we were due to go to a bunch of conferences and speak to a bunch of people at conferences, and then, like, COVID-19 happened, and we were like, well, what are we going to do now on the sales and marketing team? So we were like, well, we can try and run our own events online. And so that's what we started doing with MLOps Community. And we've had some awesome speakers already, and there's some videos on the website that people can catch up on the meetups that we've done so far, and please come and get involved.
Oh, so they're recorded. That's even better. So if people have missed them, they can go and check that out?
Yes, that's right. They're on the homepage.
Okay, cool. All right, another question, this time from Trip Parker. Hey, Trip. He's asking, can machine learning rank data across multiple KPIs, years, and geographic locations to determine which ones are key drivers?
Probably.
It's very specific.
Sorry, go ahead.
I said it's a very specific question. So.
Yeah, I think machine learning probably could do that. I think you need to make sure that you have like a training set of data that you want to that's labeled, so that you can say, oh, I'm going to try and make a model that's going to predict the answer to a question based on these certain sort of columns of input data, which it sounded like your KPIs or your geographic locations or whatever they might be. They might be columns of input data, and then there's a sort of column of output that you're trying to get the model to automatically estimate or classify. And so, yeah, as long as you can create almost think of it like a spreadsheet or a training set of the desired inputs and then the output that you're trying to classify. And if you've got training data which is labeled, so you've got like the right answer for each of these rows, each of the input values, then you can try a bunch of different off-the-shelf algorithms like linear regressions or decision trees to see if you can make a model that can automatically classify those KPIs that you've got. But yeah, happy to chat more about it if you want to come and join the Slack channel afterwards.
Join the Slack channel, everybody. All right, so I see we've got George Farragon here, Alice there. T. Scott Daniel has a really good question. He asks, what is the biggest mistake, and that's in all caps, by the way, so think of the biggest mistake data scientists make regarding implementation of models?
That's a good question. Well, one that I've seen cause a lot of chaos and pain in data science teams is not properly keeping track of how you came up with your model. And maybe that is kind of biased because I come more from a DevOps background, and in DevOps and software engineering, we kind of already have reproducibility sorted. And I'm not bragging, it's just because our jobs in software engineering are easier than the jobs in data science, because we have fewer like moving parts to keep track of. We don't have to deal with, in software engineering, because I have a software engineering background, you can build an application as a function of just the code that you're writing and the environment that you build it in. But with data science, of course, you're training models that depend on certain versions of data sets and all sorts of other variables like the parameters that you train the model with. And so one of the biggest mistakes I see that data scientists have is not properly keeping track of the work they're doing, basically.
The documentation, basically, right?
Yeah, well, it's kind of documentation, or rather, let's say the documentation is one implementation strategy for a solution. You could say, okay, I need to manually do all this work of keeping track of the models I'm making. Mm-hmm. And that could mean that I need to write really meticulous manual documentation for my models. And that might be, I'm writing stuff down in a paper notebook. And I date all of the pages in the notebook, like you do if you work in if you're a scientist working in a lab, perhaps. Right. Or you might say, I'm going to write down all my work in GitHub issues or Markdown and put it in version control, or maybe I'm going to use a shared spreadsheet that I share with my other colleagues, and I write down each model I create. I write down which version of the code I used to train it. I write down which version of the data set I used to train it. I write down which parameters I used, and I write down maybe some accuracy score or some AUC or some F-score. And yeah, that's one approach to the documentation. And what the value of doing that, of course, is that it gets you some way towards reproducibility. It gets you a kind of rough record of what you did to get a result if you remember to write everything down right. Right. But my view is that you should instead try and find tools that help you automate that. Because software engineers don't like zip up their code every single time they make a change to it. They use version control, they use Git, and they commit their code every time they make a major change, and then they can collaborate using that version control system. Mm-hmm. And so, yeah, I would encourage people to look at the tools that are available out there for doing experiment tracking automatically, and in particular doing run tracking. DotScience is one of those. There's also lots of other tools out there.
I'm just going to say DotScience is the one, no?
Well, I mean, I'll be generous and mention some of our competitors as well, which is like there's other companies like Weights and Biases, and in terms of data versioning, there's tools like DVC for keeping track of what you're doing. And there's MLflow from Databricks, which is about experiment tracking. But I would also obviously encourage people to take a look at DotScience, which also includes that experiment tracking aspect. But as a genuine answer to the question, like one of the biggest problems I see teams, they get into real trouble, real complexity, and especially when the number of data scientists working on problems increases and the number of models that are running in production increases, you just end up with stuff flying all over the place, like models flying all over the place, data sets flying all over the place. And if you don't use good tooling to properly keep track of that work, then you basically end up in a world of chaos and pain. And models going wrong in production and not being able to figure out like where that model came from, or even who created it, and what they did to create it.
Yeah, well, we want to avoid chaos and pain, right? So the question I have for you is, so who in the company would you say is responsible for managing the MLOps process?
Yeah, so who in the company is responsible for it? I'll try and answer that question by giving my view on what MLOps is. So I'll give a quick definition. And so the acronym MLOps, I mean, it or whatever it is, the word, kind of implies that it's machine learning operations. But I actually think it's more than that. I think of it as DevOps for ML. And so development and the operations of a machine learning model. And so it actually refers to the entire life cycle of data engineering, model training, data engineering, data versioning, model training, model versioning, model deployment, and model monitoring. Mm-hmm. And there's this interesting parallel with software engineering, where software engineering used to be really siloed. There used to be software engineers who write the code, and then operators or IT people who are responsible for running it. And so the developers, the software developers would send their program to the operator, and the operator would put it on the server, and they'd be responsible for keeping it running. And this was pretty hideous, actually, because it meant that the software engineers took very little responsibility for whether or not the software would actually work properly when it was running in production, because they were kind of throwing it over the fence. They were saying,
they were done. Obviously, they're done. They talked it over.
I've done my job, I'm going to go home. And then the operators, the IT people, are left trying to keep the thing running without really understanding what went into it. And the interesting thing that happened in software engineering and DevOps, well, was DevOps. And so the notion of DevOps is that instead of having this kind of brick wall between your developers and your operations people, that you have teams, like cross-functional teams, and cross-functional roles where people, the software engineers, are also responsible for deploying the software and monitoring it. And that actually is kind of a human problem, because it's a solution to a human problem, which is that the developers didn't take much responsibility for the running of their code, and now they do. So you can say that kind of the developers, the software developers, carry the pager. In other words, they have to wake up in the middle of the night if the software blows up in production. And that makes software engineers care a lot more about making sure they've got good monitoring on their software that's deployed. Anyway, this is a long way of saying that I think MLOps needs to also represent the same shift from data scientists being siloed from DevOps people. And instead, it needs to reflect more a culture of both data scientists getting more skilled up on software engineering and deployment, and also just the teams starting to build these sort of cross-functional teams where you have data scientists and you have DevOps people and you have software engineers, and they're all working together. And rather than like emailing the IT person your Jupyter notebook, you actually work together on setting up a sensible pipeline where you can productionize your models, and data scientists can push models into production, or at least into testing environments. And data scientists can also handle the monitoring of their models once they're running in production. So who's responsible for MLOps was the question. Everyone involved. Everyone involved in the delivery of the model. So it's the data scientists, it's the software engineers, it's the DevOps people, and it's their managers who are responsible for the actual delivery of business value using ML in the context of an application that's using ML to improve accuracy or improve automation or whatever. So yeah, I think a cultural shift is needed, similar to how software engineering and IT became DevOps. I think data scientists and DevOps people need to come together and become MLOps teams. And of course, new tooling is needed to support that, but I won't go on about that.
Yeah, thank you for that. And before I go to my next question, we had a couple of questions on the MLOps community, whether this is online. So yes, this is fully online, correct?
Yes, it's fully online.
Yes,
and moment.
Yeah, you can find the Slack channel by going to MLOps.community, right?
Yes, that's right. So yeah, MLOps.community, and I'm pretty sure it's a giant Slack icon right at the bottom of the page. Yeah, if you scroll down to nearly the end of the page, it says join us on Slack.
Awesome. And Trip has another question. He says, are there current challenges in machine learning that are beyond current software capabilities?
Challenges in machine learning that are beyond the current software capabilities? Yes. I think I think it's worth kind of caveating that I'm not actually a data scientist myself. I'm not a machine learning engineer. So
you're a startup. You're a startupper.
I'm a startup founder with a DevOps background, trying to apply DevOps principles to the ML space. But I mean, yeah, there are certainly challenges in ML that software can't deal with right now. I mean, I think one of the big challenges is dealing with, well, so obviously since like the 60s and the first AI winter, when the first AI winter was when people realized that the promise of AI back in the 60s and the 70s was never going to live up to all the hype because the computers weren't fast enough and they couldn't process data fast enough. Yeah. That's because back in the 60s and the 70s, we had really slow computers, and they had, frankly, they just had really small hard disks. And dealing with like the levels, the quantities of data that you need to make deep learning work wasn't possible back then. So that has been solved now, and deep learning is computationally feasible. Mm-hmm. But I guess there's a whole new set of challenges now around the sort of delivery of those deep learning models, and especially making them fast enough in production to actually crunch the kind of data sets that you might feed them. And so an example of that might be needing to use specialized hardware to do inference fast enough at runtime. And so there's a couple of interesting projects that are working on solving that. And I guess this isn't technically answering the question because I'm now talking about hardware, and the question was about software. But anyway, it's kind of related, which is that the GPUs are very, very expensive, and so if you're doing machine learning or deep learning that requires crunching a huge amount of like video data or image data, then you need to use these expensive GPUs. And GPUs also weren't designed initially to do machine learning. They were graphical processing units. It's kind of weird that we started using the graphics cards in our computers that were optimized for playing like 3D video games and rendering like photorealistic video games, and started using those for doing all of this massively parallel deep learning stuff. And I just wanted to give a nod actually to another Bristol startup, which is called GraphCore, because they're working on some very interesting hardware around an alternative architecture to the GPU architecture that is actually designed specifically for AI. And they have a chip called the IPU, the Intelligence Processing Unit. And they're definitely one to watch. I think that having computer architectures that are specialized to AI and the kind of sort of graphs of the kind of neural networks that are used in a lot of this deep learning, I think that will unlock it will unlock solutions that were computationally infeasible with the current era of GPUs. Mm-hmm. So yeah, I hope that's an interesting enough answer.
Yes, absolutely. I never heard of IPUs, so that's something I want to look in personally. So thank you.
Cool. Yeah.
Viresh is asking, how can I get started with MLOps? And that's actually one of the questions I had prepared for you, was if you can recommend any resources for people who want to learn more about MLOps.
Yeah, so definitely come to the MLOps community. There are a bunch of people on the Slack channel, and I'm really excited that we've seen this growth in the community in the last few weeks as we've kind of opened it up to a broader community, where people are showing up and saying, I'm working on MLOps at this company, and I'm here to share what I learned, and I'm here to learn from the community. So definitely show up and ask questions. And the idea is to foster a community of practitioners helping each other out. And so there's some interesting stuff that people have posted on there already on the forum and on the Slack channel that people can go and look through. One guy posted his roadmap for MLOps inside his company. And so it's like this big sort of virtual piece of paper with a bunch of sticky notes on it, virtual sticky notes on it, for different stages of the pipeline that you need to implement MLOps for. And then he's listed a bunch of tools that you can look out for those different stages of the pipeline. There's also a case study on our website that talks about a company called TrueLayer, who are one of our customers, and they talked about how they created an MLOps pipeline. And that's really interesting because they're not just using DotScience, they're also using a bunch of kind of existing DevOps tools like GitHub and CircleCI and Kubernetes and Prometheus, all on AWS. And so it gives a real kind of example of a real use case and how they've come up with. And I think the most interesting part of that blog post, which I just sent you the link to, maybe you can pop it on the on the bin, is kind of when you scroll down and you look at the architecture of what they built, because they've got this separate prototyping pipeline and then a production pipeline. And so they do all of their prototyping of models inside Jupyter, but then when they actually go and productionize their models, they push them through GitHub and CircleCI and then DotScience to train the models, and then they push those models into a Kubernetes cluster, and then they monitor them in production with Prometheus. So yeah, that would be a good place to look for how do I get started, basically. We also have a bunch of tutorials in our docs, and I'll share a link to one of those as well, because there's quite a fun one where you train a road signs model, and you train it to classify different German road signs, and then you deploy it to production, and then you monitor it. So I'll share the link to that as well, if that's okay.
Yep, absolutely, and I'll pass it on here. By the way, Trip said that was a great answer to the earlier question about the problems where you spoke about the IPUs. So,
oh, cool, thanks.
Yes. And while you're sharing that link, there's another question from Kadir. It says, how much should a data science or machine learning individual learn about containers, cloud deployment, etc.? Have those become necessary skills? And to what extent, and what are the career benefits of learning those things?
Oh, yeah, that's a really good question. Yes, absolutely.
Yes.
Emphatic yes. I think if data scientists are looking at how they can enhance their career opportunities, then a little bit of cloud engineering, and cloud engineering is this new phrase that's come up, get comfortable using one of the big cloud platforms, get comfortable building your models into Docker containers, get comfortable deploying them to a production environment like Kubernetes, get comfortable monitoring that model using Prometheus. Those are all super valuable skills, because then you'll be able to walk into pretty much any company that's trying to get value out of AI, and you won't just be the person who trains the model. You can also be the person that gets it running, surely in collaboration with a DevOps team and so on, but being able to speak that language of the software engineer, of the DevOps engineer, and being able to Dockerize. I mean, a great start is just like try Dockerizing a machine learning model.
Dockerizing.
Yeah.
Elaborate. What do you mean? Just using Docker, I'm assuming?
Yeah. So, and this is kind of cheeky to say this, but I would also say, and if you can't be bothered to do all of that, then you can try using DotScience, because we made it easy for data scientists to Dockerize a model with a single command, like a ds.model command, and deploy that model to a Kubernetes cluster, and then automatically monitor that model. Yep. But I mean, seriously, it is also valuable for data scientists to understand what's going on under the hood there, and to get a level of comfort with Dockerizing and deploying and monitoring models, so that you can actually get models into production where they can create business value. And to answer your question about Dockerizing, Docker is a technology that allows you to take a program that you want to run, so you have a TensorFlow model. So how do I run a TensorFlow model as a REST server? Well, there's a project called TensorFlow Serving, which serves your TensorFlow model on a REST endpoint. So then the question is, okay, well, how can I package up TensorFlow serving, which is a program, like a C++ program that compiles into a binary? How can I package up TensorFlow serving with my model in a way that it doesn't just run on my laptop, but I can also send it to production or staging? I can also get my DevOps team in my company to run it. And a great answer to that question, which is how do I package up and deploy my model, is that you can create a Docker image. And a Docker image is like a frozen, it's immutable, so it's kind of frozen image of a Linux file system. So that might sound a bit low level and a bit scary, but it's actually really not. It's just like saying, okay, so I'm going to start with Ubuntu, which, if you're familiar with Linux, you can say, okay, I want to start from a base image, which is this specific version of Ubuntu, and I want to put inside that base image, I want to put my TensorFlow serving, and I want to put my my actual model, and then I want to configure that Docker image so that when it starts up as a Docker container, it runs that specific version of TensorFlow serving with that specific version of the model, and it also runs it in a specific known context, which is, like in this case, an Ubuntu base image, so that all of the utilities available to that program when it's running are kind of pinned to that one specific version. And so if you get, so the benefits of Dockerizing your TensorFlow model with TensorFlow serving are, it will now run exactly the same in every scenario that you put it in. So it will run exactly the same on my laptop as it would if I sent it to you and you ran it on your laptop. And we would solve that problem of, like, oh, I'm running a different version of Python, or like, oh, I'm using TensorFlow 2.1 and you're using TensorFlow 1.14 and everything is terrible. And it also means that you can then deploy, so it'll work the same on my laptop as it would work on your laptop. It would also work the same when it's running in production as it did when it was running on my laptop. So you're not going to have all these headaches of debugging. Oh, why is the model not working properly when I run it for real?
But debugging is my favorite, Luke.
Oh yeah, me too. I just love banging my head against the wall.
Yeah, exactly. All right, thank you for that. Another question for Viresh: which cloud platforms are good for MLOps? Any suggestions?
So I'm personally a fan of Google Cloud. But we've made DotScience work on all of the big three cloud platforms, so Google, Amazon, and Azure. I personally like Google mainly because it has a really good Kubernetes implementation, and that's not surprising because Kubernetes came from Google, and it's actually quite a coup, really, that Google managed to convince Amazon that they needed to support Kubernetes. But Amazon, frankly, they're kind of playing catch up. I don't want to offend anyone from Amazon who might be listening to this, but their implementation of Kubernetes, EKS, is a lot harder to use than the GKE. There's so many three-letter acronyms, but the Kubernetes offering on Google Cloud, which is called GKE, is really good. It's kind of the best in class. And Kubernetes is a really important thing in terms of running your Docker containers. So once you've packaged up your TensorFlow model, for example, with your in a Docker container with your TensorFlow serving, the place that I would recommend trying to run that container is a Kubernetes cluster. And yeah, simply because Google Cloud gives you the best, easiest to use Kubernetes clusters, that would be probably where I'd recommend that people start.
Okay, great, thank you. And I know we're getting close to our time limit here. Just wanted to ask, and I know you touched on this a little bit already, but what are some best practices for implementing an effective MLOps or ML DevOps, I guess, right, as you call it, process in the company? What are some of the steps that companies can take?
Yeah, so we have this thing on our website. It's also on the MLOps Community website called the MLOps Manifesto. Okay. And the MLOps Manifesto is 4 things, and they're 4 tests. And I think that they correspond to best practices. And they are, let's see if I can do them all off the top of my head. They are reproducible.
Mm-hmm.
And the test, I talked about reproducibility before. So it's reproducibility, accountability, collaboration, and continuous.
Yes, I'm on the side. You got it right. Congratulations. I'll share a link to that as well.
Yeah, cool. And I can kind of run through those quickly. I know we're short on time, but I'll just give you the test for each of them. So the test for reproducible is, can I recreate a model that you created 9 months ago with a different version of a library, with whatever version of the code you used then, whichever version of the data you used then, and can I recreate the model to at least within a few percentage points of accuracy?
Mm-hmm.
If I can, then we've got a system that's reproducible. If I can't, because you're on vacation and I can't talk to you and I needed to ask you some questions, or because I couldn't figure out which version of the data set you had on your laptop when you did that thing, when you trained that model, then you don't have a system that's reproducible.
Right.
Accountability is about whether you can hold your models accountable for the decisions that they make. And when it comes to machine learning models, that fundamentally means what version of the data were you trained on? Because that's kind of on what basis did you make your decision, plus, of course, all the details about the model. Accountability, in my mind, is a prerequisite for explainability, which is a whole other topic. But if you can't, I think the requirement for the test for accountability is this kind of baseline of, can I determine the provenance of my model? So for a given model that's making decisions in production, can I trace it back to the specific version of the code that was used to train the model, the specific data that it was trained on, and also for that, oh, thank you. And also for that data set, where did that data set come from? The third one is then collaborative, which means that can you and I collaborate on a machine learning model without treading on each other's toes? And in particular, that means that we're quite opinionated about this. This is one of our opinions, is that data scientists should be able to use asynchronous styles of collaboration. And that means that if you're working on a model, I should be able to fork your model or fork your project, make some changes to my fork without treading on your toes. So I should be able to play with stuff without interfering with the version of the data set that you're using or the code that you're changing. And that's fine. It's easy to make copies of things, right? So it's easy to get that far. But then the challenge is, can we then integrate our changes with each other? So if you've made a bunch of changes to your Jupyter notebook and your data engineering code, and I've made a bunch of conflicting changes, can we reconcile those changes? And so you need a system that enables that asynchronous collaboration. And then continuous comes down to two different pieces. So this is kind of the best practice. It actually splits into two. It means that the model deployment process must be, it means continuous delivery and continuous monitoring. And so continuous delivery is, can I deploy my model to production without any manual steps? And that's important because as soon as you have manual steps, you have humans, and humans are going to make mistakes. And so you need a completely automated deployment pipeline. And then the continuous monitoring piece is really interesting because monitoring machine learning models is more complicated than monitoring microservices. Because with microservices, you can just look at things like the latency and the error rate for that microservice. Is it performing as you'd expect? But the problem with models, because they're built on data, you can have a model that's behaving normally in, a model that's reporting perfectly normal latencies and error rates, but actually has gone completely bonkers. And that could be because a new version of the model got deployed that actually doesn't work well when exposed to production data. Or it could be that the world has changed and the model was trained on data in kind of old data and it's drifted. And now the model might be, for example, if it's a road sign classifier, it might be looking at pictures of road signs in the snow, and it was never trained on road signs in the snow. And for some weird reason, it can't classify stop signs anymore. And so now you've got a fleet of autonomous vehicles driving around not being able to recognize stop signs, and that would obviously be bad. So that's why we need the continuous sort of statistical monitoring. Yeah, those would be my 4 best practices.
Great, thank you. And how did you guys come up with this manifesto?
By talking to hundreds of data science teams about their pain points and establishing that some of these are best practices from software engineering that just haven't been done yet properly in machine learning, like reproducibility, the whole thing around collaboration. And then some of them are specific to machine learning, like accountability of models. You don't really talk about the accountability of your software. And you also don't talk about the sort of need for statistical monitoring, like data drift and model drift monitoring, and looking at the statistical distribution of classifications. That just doesn't apply to software, but it's a real pain point in ML. So yeah, listening to the pain points of hundreds of teams.
All right, yeah, that's how I get all my information as well, just talking to people, listening to their pain points. So just to wrap up, can you just remind people where they can go to get more information about DotScience? How can they reach out to you if they have more questions? And one more time about the meetup.
Yeah, absolutely. So if you're interested in DotScience, go to dotscience.com. That's DOTscience.com. Yeah, we've got a free SaaS version. In fact, we just made that. We removed the limits on that recently, so that people can use it in an unlimited way on the SaaS version. And then if you are interested in deploying it in your own cloud account or in your own data center, then we also have plans that support doing that. Yeah, also come and there's a link to Slack from the dotscience.com, which is actually the same Slack channel that we use for the MLOps community. So the MLOps community is, we meet every Wednesday at 5 o'clock UK time, which is 9 a.m. Pacific, and in the US. And so we have weekly meetups, and we've had a great set of speakers so far. Come and join the Slack channel for the community. We also have a forum. Come and ask questions. If you're trying to implement MLOps and you got stuck on reproducibility or something, then come and talk to us, talk to the other people in the community, and we'll all try and figure it out together and help each other out.
That's a great offer. Thank you. And thank you, Luke, for taking the time to chat with me live. And thank you guys for tuning in and asking great questions.
Awesome. Yeah, thanks for watching. And yeah, great to meet you, Kate. Thank you.
All right. Bye.
Bye.